Good morning, everybody. Can you hear me? Yes. Today we have with us Miguel Cerviño. He did his PhD in Madrid, in La EF, and then moved to the Observatory of Toulouse for his first postdoc. He did the second postdoc in Garkling, in MPE. And then since 2002, he's in the Instituto Astrofísica Andalucía, where in 2007 he got a permanent position in CSIC. Now he's here in the IAC thinking about stellar populations.
Okay, thank you. Well, I am somebody, some of us maybe has seen me during several months here. I am planning to be here during the following 4 years, so okay, we will present something about stellar populations, and if you have more questions, you have time to find me, I hope, Sunday, so around. So the summary of the talks, I am going to talk a bit about the current status of stellar population synthesis models, mainly that most of you know what is that. But I want that in some way we think together about other ways to look to stellar population synthesis model. Maybe we think that they are one thing and they are not. So, well, this is the idea of the talk. So in the current status, I just to show what is the basic problem of stellar population. The issue is, okay, you have a galaxy, you have a stellar system, and you see the total luminosity from that system. You know, more or less, that this luminosity is dominated by the most luminous stars in the system. On the other hand, it's also known that the total mass of the system is dominated by the low mass stars in the system. So, okay, it's always the same problem in astrophysics. How obtain physical information from observing integrated quantities and from the luminosity in order to infer all the things that you doesn't know, that you doesn't see. For example, if you want to do dynamics, you doesn't want the light, you like the mass, etc., etc. The idea is to obtain some mass luminosity relationships, and if you know how this mass luminosity relationship vary with age, metallicity, etc., you are able to talk something about the stellar about the stars that are there and about the mass and other things. So the basic equation is this one, that, okay, you have the total luminosity that you know in a very first approximation, that is the sum of all stars you have there. It's very simple. You can also binning the stars in different way, and you can say, okay, we have a given number of stars of a given type, and the luminosity of a generic luminosity of this star of this given type, and make the sum. So if you define this type as a function of the evolutionary parameters of the stars, you can call it a stellar population. It's quite easy. So if we are able to characterize these numbers, this amount of number of stars, we can decompose this total luminosity in terms of the evolution of the stellar population. Actually, you see the stellar population, you see only the integrated light, but if you know what is the fraction of the different things there, you can know how many yellow stars are there, how many red stars are there, how many blue stars are there, okay? So you have a lot of information just from the integrated luminosity. So to do that, the first thing is express stellar luminosity and function of the stellar evolution. That is, make a change of variables and there. The other thing is change the number of stars of a given type in order to something that is related with the evolution of the system. Is generally called the stellar birth rate. That says you how many stars has been born with a given mass at a given time. It's at the end, if you put stellar evolution inside, you know what is the number of stars that you have of different classes there. And, well, you can assume that there is the stellar birth rate, you can decompose it in initial mass function and the star formation rate. And at the end, the only thing that you need to do is to, okay, make this integral, what are all the things that you have assumed, and you obtain this total luminosity that is somewhere normalized by the total mass. So in general, this is the thing that synthesis models do. And you obtain the integrated emission that is proportional, directly proportional to the amount of stars in the system. You know that all the wavelengths produce the same amount of information, or at least you assume that. There is a one-to-one correlation between different wavelengths. So if you have observation, for example, in the ultraviolet, you directly know what happened in the radio, infrared, etc., or even in gamma rays. And if you know something about some special stars that are in this population, for example, a GB star or radiate star, you say, okay, if I have one radiate star that I know that they are very young stars, this cluster have this kind of evolutionary status, etc., etc. Well, this is the basic idea. When you look at the literature in population synthesis, when you look at the developments, most of them has been done in basis of include more good evolutionary cracks, or include better atmospheric libraries, observational, theoretical, whatever. The idea is you compute all this in the code, produce a Hertzsprung diagram, and you integrate it and obtain the synthetic spectral color, whatever you want. But all the things has been always, when you're thinking about population synthesis, focus in improve the ingredients, but not exactly in the models. Well, you have a lot of application for that, and you have seen in a lot of papers, especially if you are talking about the stellar cluster and about extragalactic astronomy, about cosmology. But the basic idea is, okay, I have the total luminosity that I have obtained it. That is, you can compare it with the observed one. If you make a color, this dependence of mass, pairwise it, and you obtain the age and the metallicity of the population, and from the normalization, you obtain the mass of the population. It has been done in initial mass function study, photoionization modeling, star formation studies of the universe, Kenny-Cat, Mayo, etc., photometric redshift, a lot of things, okay? So this is the general status that you always see in population synthesis. The problem is that there is some people that are detractors of synthesis model that say, how do you propagate uncertain? The model results are dependent of the modeling. There is a lot of things. There is a problem there because, okay, you have all this mathematical thing, but it looks like magic, and you obtain a lot of things that the people doesn't understand what happened there. And in fact, there is some fuzzy cases where it's not so clear how to match with population synthesis. So I will show you some example about that help us think about what is going with the thing we are doing. This is a case that happened to me when I was making my PhD. Box 186 is a dwarf galaxy that is very young galaxy that is very close to Spica. And okay, we make a UV observation of this galaxy, and we obtain it was interesting because it was a world-radiate galaxy, so it was supposed to be young. We make a fit, we obtain a very, very good fit, but the age of the fit and all the things was a bit older. So it looked that you have a dwarf galaxy that is in an instantaneous course of star formation, but the continuum comes from another population, so it was an extended star formation, something like that. But there was a problem. That actually, IUE at this moment has a small hole there, and there was a lot of diffuse light from Spica, and the things we were fitting, and the fitting was very, very good, was not this galaxy, was Spica. And the age we obtained it was not the galaxy, the age of this galaxy, was the age of a stellar population dominated by Spica-like stars. So, okay, well, we doesn't publish anything about this thing because for other things we already that there was a problem there. But the issue is I have applied the model to a single star, and I obtained a good fit. So Well, when we talk about synthesis population, there is any difference if you have 1 star or 100 star or million hundred stars, or you can apply the model to 1 star, for example, or 2 or 3. What are the difference? Because you fit and you obtain good things. So, well, this is another example. This is from an 82 stellar cluster. Here, thinking a bit about, well, what is the things that are obtained by synthesis model and the things that are single star. I plot here, this is the for a single stellar population model, that is an instantaneous course of star formation, how the cluster must be depending of the age, okay? And we plot here what is the position of in this color diagram of individual stars. You say, okay, models are here, individual stars are here. If you go to the cluster, okay, first you have a lot of scatter. Okay, you can say, okay, this is a problem of extinction, whatever, but even if you have a very good facility, etc., you still have scatter. So with just this model or this value of the model, you cannot cover all the parameter space that are covered by the real cluster. And they are clustered. Some of them looks like individual star because they are dominated by the individual star, but there is something in the modeling. Maybe we are making an assumption that we have this amount of star, this other amount of star, this other amount of star, and maybe it's not so big. There is a small amount of star somewhere, and it makes that the color diagram you find is not so good. Your results are not so, the result of the synthesis, well, okay, they are good, but in some way, in average. But actually, if you forget, well, a bit about observation, this is from Russell in 1882, well, in this year. And this is another color diagram. The big dots are a small Magellanic cloud globular cluster. The lines are the results from single stellar population, and the dots are Monte Carlo simulation using the same code. The same code, everything is the same, but the only thing is taking into account that you have a discrete number of stars. That if you say, okay, I have a number of stars that is 10 to the 6 solar masses in each point here, this is the distribution of point you have. And it is the same code. So, okay, well, depending if you make the integral in one way, or you make the integral making a Monte Carlo simulation that at the end is other way to make this integral, you obtain different results. What is going on there? And of course, if you go to lower and lower stellar masses, one thing you see is, okay, you have here more or less is in the middle, but if you go to lower masses, there is the simulation goes away from the models. And if you go to very lower stellar masses, actually, if you plot here individual stars, you see a lot of clusters that actually they are clusters, but you look they like individual stars. So how to manage that? One solution that some people have said is, okay, all the things we know about population synthesis is only valid if you have a very big system. Well, maybe, but if you look at the formulation, you say, okay, here there is nothing that says that it must be a big system. So it's something strange. The other thing is that maybe this formula is not the thing that you think it is. Maybe you think this is a varita mágica, but in fact it's not. Okay? Only you like to see it like a varita mágica, but it's not. Okay, so let's see what will happen there. Okay. Let's think. I'm back to the very origin of the problem. That is that. Okay. Well, we have the total luminosity is that, but one thing we can do is, okay, we can divide this by the total number of stars, for example. The formula is still exactly the same. And now what you obtain, if you do that, you take the sum of all stars and you divide it by the total number of stars, you obtain the average single star luminosity. Okay? And it is an exact result. If you obtain the mean of a population and multiply it by the numbers of elements in this population, you obtain the integrated quantity. In the other hand, if you think, actually, when you are talking about the stellar birth rate, well, there was this thought about the number, about the mass, that how it's work. Actually, we are so intelligent that we are able to say exactly how many stars are in a galaxy? I don't think so. But from a stellar population, we can say about what is the fraction of different amount of stars. And from star formation theories and complexity and other things, we can say, okay, we can model it as a probability distribution. We cannot say how many stars are in some way, but we can say, what is the probability of find one star with this mass or with these evolutionary stars? That is a very different question. In this case, the thing that you obtain is the average mean luminosity of a single star that is taken from all the sample of stars you might have in your galaxy. It is not an integrated luminosity, okay? Actually, it's a description of the mean of the distribution of possible stellar luminosities. But it's very different to thinking about single stars or total number of stars. Okay, but we apply it to big system, to stars to galaxies with a lot of stars. So, if you think in this way, okay, you can make, for example, this is a Monte Carlo simulation that actually is the stellar luminosity function. If you take one star and you put it in the EMF and you evolve it, this is the different amount of stars that you have at different luminosities. Okay, this is for a 10 megayears cluster. It's very funny. You have most of your stars in the main sequence. You have another stars in the, well, near the making some loops in the H-or diagram, and you have a lot of stars in the red supergiant phase of the diagram. This is what's happened going star by star. You can say, what is the probability to have a red supergiant? You look here, and it's something like 10 to the minus 3, okay? If you now make simulation using not star by star, but by group of 10 stars, 10 stars, 10 stars, 10 stars, you obtain something like that. That, okay, you say, well, this one, they are similar, but it's something screen. Well, they are always normalized to the mean luminosity. So, well, okay, when you go from here to here, the scale decreases in a factor 10, etc. And if you go to 100 star or to 1,000 star, you obtain distribution of these ways. Okay. Can we relate all these things? Actually, okay. Think of it. You talk about one single star. If you have a one single star, you have this probability distribution. If you have two stars, the total luminosity for a given luminosity is the probability that you have one star with a given luminosity multiplied by the probability to have a star with the luminosity that is needed to reach this luminosity. That is actually the convolution of these quantities. If you have any n times in stars, at the end the distribution of total luminosity are n times the convolution of this stellar luminosity function. Okay, what's happening with one star? Okay, you can see it. Or This is for another age, but in any case, this is the same simulation I showed you, similar simulation I showed you before that for Monte Carlo simulation of cluster. Here we just take, okay, we will mimic this part of the distribution that are main sequence star by a Gaussian distribution, and this part of the distribution that are red supergiant star, but this kind of distribution, and began to make convolution of it. If you take this function and convolve it 10 times, you obtain the red lines. And if you compare with the simulation, well, they are quite similar. And if you do it 100 times, you obtain that. And with 100%, you obtain that. You are recovering what is happening in the Monte Carlo simulation analytically. So it's quite interesting. You can understand, making that, what is going on inside the Monte Carlo simulation. Actually, you can say, okay, I have here something like one red supergiant. This is one red supergiant also. These are main sequence star. I have one red supergiant. I have two red supergiant. That if you have 100 stars, the probability is a bit lower. You have three red supergiants. And here you can see main sequence 1, 2, 3, 4, 5, 6, 7. Red supergiant are very, very luminous. So it's very different if they are there or if they are not there. And only, of course, if you have lot of stars, at the end you obtain Gaussian distribution. Okay, so to have one star more, one star less is not so different. So the thing is, okay, you can relate what happens with the stellar things and with the population. You can obtain the mean value of the luminosity, stellar luminosity function. If you multiply it by the number of stars you will have, you obtain the mean value of the total luminosity. You can also work it with the variance of the distribution, because it's not only the mean. Most of the model only produce this mean, but they can produce the variance, the squeezeness, the kurtosis. So you are mapping the distribution and you can do it. The important thing here is that, okay, in the first case, in the observational case, you observe the total luminosity, and in some way, in order to make the fit, you are making an estimation of the mean value. If you take a color, you divide it by different wavelengths, so you obtain a color that actually is independent of the total number of stars, but this color is not exactly the color that you obtain when you work theoretically. This is an estimation of the color that you have from the observation, and this is the mean value for the theoretical population, for the theoretical distribution. So the problem actually in the fitting of models is how much these mean values that you some way obtain from observation can be compared with mean values that can be obtained from a standard synthesis model. And always, when you have a synthesis model, you obtain the main result. This is the mean. The total luminosity you will obtain from a galaxy is around this mean. But you must know how is this distribution to say what around means, okay? In order to show it in another way, you can think, okay, I use just the mean value of the model. So I have three models and I have here my observation. What do? Is make a chi-square fit, and you say, okay, this is the closed model, and I publish my paper, full stop, okay? If you take into account that the accuracy of each of these possible mean values can be different, if you vary the age, for example, you vary the mean value, and you also vary the distribution that you are working on and other things. So every time you make something, you are working, you have a metric of fitting below. And this metric of fitting you must think in order to make the models. And in this case, for example, if you have this observation, okay, each one is the more close model. If you take just in consideration the mean value, but if you take into account that the dispersion that is intrinsic of the model, the variance that is intrinsic in nature, it turns that this model is not compatible with the observation. And this one that actually was the farther is the one that actually produced the more accurate result. Maybe it's not precise, but it's the better you can do. Okay? And we are in science and not in mathematics, and we worry about accuracy, not about precision. We want the two, but it's better to have accuracy in any case. This is another example of this. You have here the mean, well, and the spectra, that is the mean of any synthesis model, whatever the model. You have here the variance, and it's a bit funny because, okay, you see here different absorption lines. Okay, this one is it's gamma, I think, or it's delta, and this is, well, another one. If you make a fit of that, if you assume that you must fit everything very, very good, you will obtain a result. But if you take into account that maybe there is difference, because here there is the contribution of one kind of stars, here in the continuum there is the contribution of another set of stars. In other parts are the contribution of another set of stars. This contribution vary in number. So the dispersion vary in number, and it is intrinsic. So you can see that this part of the spectra might have more scatter. This is the variance that the other parts. And if you take into account also the squeezeness and the kurtosis that see you how deviate from a Gaussian, it looks like, okay, to make a very good fit to H, whatever, it's delta, I think. If you fit very good the profile of H delta, but you doesn't fit the continuum near H delta, your fit is bad. You are making a bad fit. The thing you must fit the first is the things that you have a lower dispersion. And then go on to other things. Actually, it can be seen in another way, that is surface brightness fluctuation, that is an observational fact. If you have a galaxy, you say, okay, I have all my galaxies, you take the model and you obtain an average galaxy, subtract it, and you see that there is fluctuation around in the pixels. So one way to use that in order to fit models is to Tonry in several years ago, he realized that if you use the variance of this distribution of fluctuations and divide it by the mean value, you obtain a quantity that is independent of the number of stars you will have in the pixel. So it proposes it as an universal handle, okay? But if you look to surface brightness fluctuation in a probabilistic point of view for synthesis model, you can say, okay, whatever you do, even if you have infinite stars, if you make, instead to make a fit to say, okay, my observation, my model, you make a fit in this variable, this is the residuals you will have. So you can fit at the same time your observation and the residuals of the observation, because the residuals have some physics there. Actually, if you do that, you can break its metallicity degeneracy. It was shown by Buzzoni in 2005, or before actually. But this is a case of its metallicity degeneration. This is for 2 gigayears cluster and for 15 gigayears cluster. If you just fit the mean value, you obtain it. Okay, they are very, very similar. But in terms of the possible fluctuation you have there, the spectra is very, very different. So it breaks its metallicity degeneration. Actually, both in 1984 proposed it, but well, the way they proposed is not, they was not thinking about synthesis model in a probabilistic way. They will say, okay, this fluctuation is due by Poissonian statistics in number of stars. So So it's different, but the ideas there that can break stellar metallicity relation and why remains the same. And if you think, okay, well, when we are working with the models, actually we are doing something very, very similar that is done in color magnitude diagrams. In a color magnitude diagrams, you obtain, well, you take the stars, plot it in a color magnitude diagram, and fit to all the isochron. Okay? If you just think, you can say, okay, I can take all this thing and fit to the mean of all this isochron. Or you can say, okay, I know that the number of stars here is different than the number of stars here, the number of stars here. So you have a luminosity distribution function. And actually, the people that makes a color magnitude diagram fitting takes into account not only the stars that are somewhere in the diagram, but the stars that are there in taking into account also all the other stars. The fractions are must be similar, must be something there. Okay, and if you take into account all the information you have from all these stars, not individual star by star, you obtain these star formation rates, metallicity distribution, etc. The only difference here is, okay, synthesis model works with parameters of the distribution. Most of the models only produce the mean, but you can also produce variance, kurtosis, all the things to parameterize this distribution. But actually, it's the same thing in a different way, in a different view. Okay, and now, okay, when you talk about, usually when people think about color magnitude diagrams, say, okay, we know all the individual stars. And at the moment that you doesn't have individual star in your resolution element, you think about population synthesis model, blah, blah, blah. But if it is the same and they are distribution that connect what happens with one star and what happens with different type of stars, you have a way to connect all the things you can do with color magnitude diagrams and also with population synthesis. And you can work, you can say, okay, this is a galaxy, this is a pixel by pixel distribution of the colors in these galaxies. And here you have, okay, it's not a color magnitude diagram in the sense of stars, but taking into account what happened in each of these pixels and taking into account the global structure of this diagram, you can obtain things about a stellar population of that in a similar way that you can do in color magnitude diagrams. Okay. Well, it's also can be, if you're thinking also about the case of IFUs and current facilities, the issue is, okay, we are increasing a lot with big telescope the spatial resolution. When you increase the spatial resolution, the point here is not how many stars are in this galaxy, but how many stars are in your resolution element of this galaxy. Okay? So if you increase the spatial resolution, you decrease the number of stars that you have in each resolution element. So instead you have a mean value, more or less Gaussian, you begin to go to distribution that are not Gaussian, etc. And you can use this distribution and you have more information about the stellar evolution in the sense that if you know these distributions and you are sampling this distribution and you can fit the shape of this distribution, it provides much more information that just fit the mean value. Okay? This is just another example. Is, for example, if you look to galaxies, you take two luminosity profiles. People that has been working with that, it's a very funny thing because, okay, you have here the profile, and when you go to the border, well, increase a lot the error, or the people say that this is the error. It's a bit funny because they take the more or less. You can assume this is an elliptical galaxy. You can assume that the number of stars more or less in each isochron in each radio is similar by dynamics arguments, but you have this scatter. Actually, you can think about that you are going from a Gaussian regime where you have a lot of stars to a non-Gaussian regime with a distribution that have different shapes, etc. And this thing might contain some physical information. It's not just error. If you have a perfect telescope without errors, you will still obtain that. So here there is a lot of physics, and we can find it, and people forget it. Other things that you can do with that. For example, in a probabilistic description, you can include fast evolutionary phases, or you can include things where the luminosity varies with the star. Usually in the model, you assume, okay, if I have an initial mass and the age, I have one and only one luminosity. But if your star is variable, actually you doesn't have one single luminosity. You might have several luminosities, a distribution of luminosities, and the distribution of effective temperatures, etc. This is, for example, the case of thermal pulses. This is different kind of thermal pulses. They are very, very quickly, okay? So you can say, okay, if I want to follow these thermal pulses, I must to make a model with this time resolution that is crazy. And the other thing is to thinking about what happens with this kind of individual stars to say, okay, in my time resolution, in this time scale, I know that the probability that the star is in this part of the thermal poles is this one. In this other part is this one. In this other part is the one. And you can include it in the model. Okay? At the end, the only point is don't to think about how many stars can be in a given phases, but what is the think just about single star and think what is the probability that the star is in this single phase. So, well, with these ideas, you can obtain not just the mean value that is usually done, but also the variance of the things. And as far as you are beginning to include distribution, you can also compute the errors that are in the evolutionary cracks and the errors that can be in atmospheric libraries, etc., etc., etc. And you can provide also the systematic errors that are everywhere in the model. So, and maybe I'm sure that if one take into account all these things, most of the modeling, Bruthal and Charlotte, Klaus Leither, Alex, whatever, obtain a very, very similar result, because at the end the physics are similar, okay? They are the same physics, so it's at the end doesn't matter which model you use. So in a brief summary, and well, I have a few slides more, but the synthesis model just reproduces the mean value of the emission of individual stars. The integrated mean values are proportional to the total mass of the total number of stars, but not the actual values. Different wavelength provides different amount of information, and you must take it into account in order to make the fitting. And one bonus crack of that is if you take that into account, something like its metallicity degeneration, etc., can be broken. And I will try to go very quickly. Here, the only thing I have done here is, okay, there is a probabilistic framework to make the modeling. And I say, well, with the model, you can obtain a probability density distribution that things happen in a given way. But when you want to compare it with observation, there is some subtle things that people some way forward. Usually one thinking, okay, I can, you are working with a statistics problem. And I have given you a probability, the probability results. But it's not exactly true because when you make the fit, you are assuming yet what is the initial mass function, what is the star formation rate somewhere. So it's not exactly a statistical problem, but it's not a testing hypothesis, but it's a problem that is more related with conditional probabilities. I will go more quickly. This is a paper that we are in detail, but just I think it's a good example. Let me just put it. Suppose you have a sample of n stars. And, okay, if an event with a probability P occurs typically n times P. Okay, if we expect to have just one star in the range, here is the initial mass function, for example, in between the upper mass limit of the initial mass function and a given mass limit, you can put this equation. Okay, you can solve it because you know the number of stars and you obtain a mass value. And now, what is this in value that you have obtained? Is actually the most massive star that the cluster can host or not? You need to make some things about probability, etc. is not trivial. But the question is, if you do it correctly, at the end you realize this is the distribution of possible maximum, the possible values of the maximum mass that a cluster can host for a given number of stars. This is the value that you obtain from this equation, and you realize that this value exactly produces the 7.3 percentile of this kind of distribution. Okay, now think in another way. We have a sample when we observe the more massive star in the cluster. That is a quite observational issue. You go to I don't know, always you can see the most luminous stars that are the more massive one. What is the number of stars and hence the mass that you have there? Okay, you put this in the equation, but now you doesn't know that, and you know what is this value. What does mean? Okay, in order to solve this equation and give a meaning to that, you must use the bias theorem, etc., etc. And if you assume that the possible number of stars is a power law distribution with a exponent beta, at the end you obtain that the mode of this distribution that is compatible to have an observed maximum, an observed that with a given maximum mass is given by this equation that is very, very similar. The solution of that is very, very similar of that. So the solution of this equation actually is just the mode value of the distribution of the number of stars for a given observed maximum mass. If the distribution of unconstrained distribution of possible total masses is flat. It's, well, this is just one example to show it, is depending what are the things, what is the knowledge that you have of the system, you can have distribution of this way and distribution of this way. Well, they are changed, the axes, but actually they are very different ones. And if you want to make a testing about what happens with observational data, you must to be very, very sure of what is the distribution you want to test. Well, this was another example of inference problem that you have this thing here, this person here, and you want to know what is the nationality of them. So, okay, if you go there, you say, okay, there is one woman, 3 children, more or less, for the fertility rate is something like 3. So this person is from Peru. But if you take into account that the rate between males and females is actually 1/2, there must be an observed person there. So actually, this person have not 3 babies, but have 6 babies. So all of them are from Uganda, okay? Actually, they are from France, Mexico, Spain, Italian, but not from these places. The thing what happens here is, okay, first, they are not black. They are not in a place that looks like Uganda. They are not looks Ugandan people, so maybe they are not from Uganda. Okay, you have much more information here than the one that is used in this example, and we doesn't include this information. So we obtain a biased result. In other way, if you are talking about this kind of things, whatever big capabilities in telescope or whatever, the inference you can have about the stellar population, about the star formation of the universe, whatever you want, depends of how many information you include. If we are now in a situation that there is very large telescopes, you have more global information that we are thinking. If you go to this galaxy and only consider pixel to pixel and make a fit of pixel to pixel things, okay, you are losing what happens in the global thing. And this global thing is giving you more information than you think. So the conclusions are here that, okay, more or less color magnitude diagram and synthesis model are equivalent. Actually, they model exactly the same. The point in color magnitude diagrams is that they use the world distribution, and usually the people that use synthesis model only use the mean value of this distribution. But any case, if you think in probability terms, synthesis model can be also used to describe the distribution of integrated quantities, and you can extrapolate all the things that you do with color magnitude diagrams also to modeling galaxies. And much of observation now with current facilities are in a situation where we are not have a fully resolved stars, but we are not fully integrated star. We are intermediate, and we can take advantage of that. Also, there is an intrinsic physical variance that in all this modeling. At the end, you doesn't know which stars are there. So the only way to model that is assume that you have a variance. Okay? And this variance intrinsically define a metric of fitting, and you must use it in the fitting. Well, this framework also provide a way to include systematic error there. And finally, the results depend on the amount of information you use. You always can use, the problem is always you will use the bias theorem. People are not aware what they are making inference, that at the end they are using the bias theorem. And well, if we are aware, we can do a better science, I think. So sometimes when people make criticisms, some kind of criticism about synthesis model, that they are good, they are bad, maybe they use the model like a black box, and they obtain things like balls, stars, more balls, more stars, even rabbits, and more rabbits, and they doesn't understand what's going on, and they think that they are magic. But actually, there is no magic at all. And that's all. Thank you. Pobrecitos.
Thank you, Miguel. Time for questions.
I totally agree with your last point number 6, in the sense that we always use Bayes' theorem, even if we are not aware of that. During your talk, I was thinking about the fact, look, this is the typical or the kind of inversion problem in which Bayesian framework could be used. And at the end, you have shown some results. And I think that it was in the slide 4 out of 5 in your inference problem that you showed. I don't know whether I understood, but apparently your inference depends on the prior information.
Yes, always.
So in my view, this just means that you don't have enough information from observations. Is this true?
Yes. The question is, well, there is this paper that Nature Physics, Albert Antola, that it's very funny. If you think about the problem of inference, actually, if you think about Popper and things, you can never verify anything. you only can falsify things that are not correct. So the way to do that, to make inference is, okay, you always assume a prior. So you make the inference with your prior. You obtain one result, and this result also might affect the prior. You can use it. So you began to iterate, and at the end, the thing is you must obtain a result where the prior and the thing you obtain are self-consistent. As another example, if you go to this slide, this is, okay, these data points that are observational data points with the total mass of, with the maximum mass of a star in a cluster and the number of the total mass of the cluster. Actually, these total masses has been obtained assuming that there is a flat distribution of a possible number of stars. But when you plot this number of the distribution of this number of stars is a power law. So the thing you can do to obtain, the data is not consistent with itself. So you must do, okay, use this prior now, make another inference to the total mass, and iterate until you find a self-consistent solution. You cannot assure that it is true. You only can assure self-consistency. And yes, and always the data, there is something that you doesn't know, and there is no way to escapar de eso.
Okay. Suppose that you have a typical spectrum, say resolution 2000 of a stellar cluster in a galaxy with a signal to noise ratio of 20. So when should you start worrying about these effects of a finite number of stars? What is the mass of the cluster at which all these effects are important? Could you give us a...
Yes, it's depend on which a lot on which wavelength you are looking for and what is the kind of spectra you are looking for. In any case, if you have the spectra for the fitting,
so when the variance due to the fact that the number of stars is finite is smaller than 20.
I need to make the numbers. I don't know.
But it's 10 to the 5, 10 to the 6 solar masses, 10 to the 4?
I know the more or less. I know if you have a 10 to the 6 solar masses and you are working in the infrared, you have problems. Because, well, there is another way. Valentina and myself make a paper out the lowest luminosity limit that is compared to the most luminous star you might have in your model and the luminosity of the cluster you have. So, well, it's a way to say where you have, when you have problems. But any case, the thing here is it is not exactly, if you have sampling problems, you are in very trouble. The better thing is to make convolution and Monte Carlo simulation. If you have a very large number of stars, you still have a distribution, and this distribution is Gaussian. And even with an infinite number of stars, you have a Gaussian distribution. And the variance that you have, the metric of fitting, the thing I showed you with the surface level fluctuation, this is independent of the number of stars you have. The way of fitting, you always must care about this metric of fittings. If you have a low number of stars, you have also another problem. That is that this estimation of the variance you will have is not a Gaussian distribution, so it's more difficult to make. Actually, the chi-square fit doesn't work because chi-square only works for Gaussians. Okay? I don't know if I answer you.
In fact, following with this, I find it a good example, the surface vacuum fluctuations. And in fact, you mentioned its power, this entanglement and metallicity, taking into account of this statistical.
Mm-hmm. Yeah.
So but just on along these lines. I mean, the most important thing here is the second order luminosity. So
Yes.
Exactly. So the brightest stars are the ones that are making the difference.
The brightness star, when you compare it with the global, is not that's the point. Is you must to take into account all the distribution, not only the brightest star. Usually, people thinking about software brightness fluctuation only think about the brightest stars, but it's not. It's the brightest star and all the low mass stars.
Of course. But I mean, the ones that count more by far, because you are at the end is the square of the luminosity.
Yes.
So it is the brightest stars. So the point is that those are the ones that are let's say, less well-known stars to some extent. Bulging, okay. So these are the one at the end effects that count, and that this power for the centennial age and the metallicity is becomes diluted. Well, there is a range of course, of all populations becomes easier in that sense, and maybe you cannot go to your population to apply this kind of approach. But my point is that there are other issues that, and this is a good example indeed, that the ones that count more and the ones that really are driving the uncertainties in this kind of inferences.
Yes. No, I agree. I also to show you that the thing here that depending how you the point to do that is not only to make inference but also to include all these uncertainties in order. Okay, at the end, their models will not be a single spectrum, will be a band, well, a distribution for each wavelength. But is the real thing you can do. And other thing is something like magic and mathematics.
Okay, well, now there's the scientific coffee. So let's thank Miguel again.
Me lo quito.